Good afternoon, fancy meat computers. How is everybody doing on this very rainy, wet, soggy fall day? I hope, if any of you are on campus, that you're using the tunnels and the bridges on a day like today. There we go. Alright. Is that too close? Close? There we go. Alright. Wonderful. So, in terms of you are dead. Okay. Moonstar is dead. If you're dead, then how did you type that? Logic. Can't get you that way. Alright. So, with respect to announcements, I posted some extra resources that should help get you started with Haskell programming. And I'd just like to review that information before we get into our lecture today. So, everyone is trying one-line solutions. That's funny. Okay. Alright. So, under Avenue, I've collected up a few resources for you guys, which hopefully will help you start getting some poltergeist. My god. This should help you to get some... all solutions can be one-line solutions with semicolons. Yeah, it's a little trickier in Python, but yeah... At a certain point, you start with just programming in another language that has a dirty, rotten name that I can't say on stream. Well, I could say it, but I'm not going to. There you are. Anyway. So, I have added a new section to our course materials on Avenue called Learn You a Haskell. Because we are going to learn you guys a Haskell for great good. So, those resources are a YouTube video where one of the people who worked on Haskell explains why Haskell is cool and good and why it exists. The next is I would expect the bulk of the Haskell learning should occur in this one. This is a 1 hour and 16-minute video called Haskell Tutorial Learn Haskell in One Video. So, I have reviewed this video, and I can say with confidence that everything you need to know about Haskell, that to do anything you would need to do in this class is covered in that tutorial. So, basically, last time when we were talking about Haskell, last time in class, it was kind of like the slides of Curtis Dalvis, who is or Dalves, I'm never quite sure how to pronounce his last name. Anyway, he's a PhD student in the department who has taught 1JC3 in the past, I believe. And he has a series of videos on his YouTube channel that are also aimed at learning you a Haskell for great good. However, basically I was like, okay, so these are videos, this would probably work, but can we find something better? No disrespect to Curtis, of course. But his videos are primarily aimed at a first-year or entry-level audience, whereas you guys are no longer first-year or entry-level. You guys are in your third year and should be able to tolerate the video I have linked in this thing. Yeah. Also, 1XA3. Yeah, he used to teach at 1XA3. Yeah. I kind of teach that course now. It doesn't exist, but it was split into 1XC3 and 1XD3, and I teach 1XC3, and it's a fun course. I like it. It does C programming now, though. It's like they took the first half of 1XA3 and combined it with C programming, and that's a course now. It's the second. No separation between the characters D and A. Dalves? Okay. Okay. Dalves. Thank you. Thank you, Moonstar. So, so that's this video. Highly recommend watching it from start to finish if you're not... it's even very good Haskell review if you already know Haskell. So, there we go. I'm not going to assign it as mandatory viewing because I don't believe in assigning mandatory viewing outside of the designated class time. It smells a bit too much like getting people on the internet to do our teaching for us. So this is an extra resource. We will be covering this type of material very similarly and probably, over the course of the next couple of tutorials, the next couple of weeks. So we're going to try to make it so that the tutorials are all you require. However, it's good to have extra resources, so here are your extra resources. Further to that, I have posted a link to a textbook, because I know how much you guys love textbooks. This is the textbook I used to learn Haskell myself a number of years ago. It's called Learn You a Haskell for Great Good, A Beginner's Guide. This is also targeted at people who already know programming and want to pick up Haskell. The whole thing is online for free, so you don't have to buy anything. It's got fun illustrations as well as like the Minecraft pig. So yeah, Learn You a Haskell for Great Good. It's a real it's definitely the best textbook on Haskell. I wouldn't even call it a textbook. But yeah, and if you want to buy it outright, it's not that expensive either. But yeah, that's how I learned Haskell, so that's how I'm transferring you knowledge to. And I also found, in case you guys want some practice problems, I found this website, which is done by the Haskell people. It's 99 Haskell problems. So Moonstar, don't do them all at once. But yeah, it's like problems with solutions. Fairly complicated ones. You don't have to do all 99. In fact, I'm not assigning any of them, but people sometimes ask for questions, so there are some questions for you. So yeah. So there are some Haskell resources for you. This should be enough, like if you go through this carefully and, do this keeping in mind what the questions are asking, you should be able to come away with everything that you need between these two videos to be able to do the assignment, and that's not too bad. Like the problem with Curtis's video series, like I took measurement. I looked through his series of videos, and in order to get in order to reach a similar level to this video here, you would need to watch at least 3.5 hours of his videos, and I figure if I can get that information into you guys in 1/3 of the time, you would probably appreciate that. So that's why this video as opposed to Curtis's. So yeah, there we go. So yeah, good, cool. So let's move right along with our lecture material today, shall we? Unless you guys have any questions. Might be appropriate to ask for questions at this point. No data. Steven says, I would recommend watching the first video of Curtis's just to install Haskell if you want to use VS Code. Yes, okay. When will the IA2 Dropbox be posted? When your professor remembers to do that. Alright, Doop. Shouldn't take a moment. A2. I forget what it's out of, so we'll just say 10 for now. Save and close. Make visible. There you go. You got to see behind the curtain. A2 is due this Sunday. The assignments, there are 10 of them. They are weekly assignments, and you have 1 week to work on them. I'll be popping on Piazza this afternoon to clear up some of the questions up there. So, good, excellent, wonderful. So, when we last spoke, we were talking about semantics. We were talking about the various styles of semantics, just to go over them briefly again. Operational semantics. The point of operational semantics is that we are defining the behavior of an abstract machine. We would define the behavior either in terms of single steps of evaluation or in whole steps of evaluation. That corresponds to small versus big step semantics. Denotational semantics, on the other hand, focuses on drawing correspondences between terms of the language and different semantic domains. This is very similar to the idea of taking successive applications of the successor function to 0 and interpreting that as mapping to the natural numbers. There we go. The interpretation function maps terms of UAE to n. If I put the dates in the PDF, then I have to modify them every year. Denotational semantics. That's the next. Or no, we did denotational. Next is axiomatic semantics. Operational and denotational semantics start with a language behavior and then derive laws of reasoning from these definitions. Axiomatic semantics work in the reverse direction. We take the laws themselves as the definition of the language. This means that the meaning of a term is precisely that which can be proved about it. This normally takes the form of assertions about the modification of program states made by program instructions. This approach is closely related to Hoare logic. You guys would have done Hoare logic, I imagine. Let me do a poll. Y'all remember Hoare logic? Use today in an equation in text and just recompile. It's too much work. Okay. You don't know what Hoare logic is, okay. Okay. So, Hoare logic. You also may have heard it referred to as Hoare triples. This isn't actually a major topic in this course, so I'm going to just gloss over it, but here you may want to know this for future third-year courses. Wink, wink, nudge, nudge. Pretty sure, anyway. When you have... so what a Hoare triple is its precondition, statement, postcondition, right? So the precondition is some kind of statement in formal logic. Normally, you would be making this statement in something like predicate logic. The statement is, that is a statement of the language, proper programming code, and then the output is the post condition. Like the post condition is the last component of the Hoare triple, which yes, yeah. Dr. Call will find you and he will end you if the results of this poll ever get out. So basically, you can demonstrate interesting things with this. Like, for example, if you have a safety property that's been expressed in formal logic, you can put it in the precondition, you can put it in the postcondition, and then you have to have some kind of like deductive process by which you derive the postcondition from the precondition. So it's kind of like this. Hoare triples were the foundation of calc checks while loops. Yes, it's probable that you just don't know the name for it, but yeah, if you took Dr. Call's class, I'm sure you did them. I'm sure you did them well as well. You probably just need to connect the intuition to the actual name for them. And it's easy to remember because it's funny, even though it's a person's name. Don't laugh at it. So, semantic cage match. During the early development of these semantic styles, which was through the 60s and 70s, operational semantics were generally regarded as inferior to the more abstract styles. Denotational semantics, as a style, had a tough time dealing with concurrency and non-determinism, however, which is fatal in the internet age. So, essentially, originally, operational semantics were considered the bad, like the horrible, bad, like, why would you do it this way kind of way thing. But then it turned out to be the only style of semantics that managed to survive. Because denotational semantics doesn't deal very well with concurrency, which, given how much concurrency there is now in this web-connected world of ours, denotational semantics fails to address a lot of problems. And then axiomatic semantics ran into similar problems with procedures. In reality, each of these styles made contributions to each of the others, but operational semantics eventually won out because of its simplicity, which should be a lesson to all of us. That which survives is not always the best, most complicated solution, but the best and simplest solution. In this course, we will be using operational semantics exclusively. That's true. The question asked if you remember it, not if you've done it. Fair enough. Although that might be more useful to know. So, here are the operational semantics of the Boolean subset of untyped arithmetic expressions. Okay, memorized them? Okay, next slide. Just kidding. Let's go through them. So, first of all, I'll preface this by saying what I mean when I say we're just dealing with the Booleans. You may have noticed with our untyped arithmetic expressions that half of it was dealing with Booleans and the other half of it was dealing with natural numbers. With this, so actually, we're going to be dealing exclusively with Booleans until we hit arithmetic, like right at the end of this set of lecture slides. So, get used to this, basically. So we will define a sublanguage of just Booleans that has only 3 terms. Could I make the slides larger? Boop. Let me see. I could probably do that. View. Presentation. There, that's a bit better, yeah? Yeah, that's probably considerably better. Shush! Thank you. So, we've got 3 terms. We will be dealing exclusively with 3 terms for quite some time. True, false, and if-then-else. Of these, we designate true and false as being values. The correct way to think of this is, of the terms, we are specifying a subset of the terms which constitute values. Now that we're talking about semantics, we are interested in making a distinction between compound terms and terms that are irreducible. So true and false are irreducible, right? There's no rule we could think of that would reduce true to something else because it's intended to be the stopping point of term simplification. So we call it a value. Next, we have, let me just move this like that a little bit. Okay, good. Next, we have our rules for evaluation. So our semantics of Booleans is comprised of a syntax along with rules for evaluation. Remember, the rules of evaluation operate on an abstract machine, which the state of this abstract machine is the terms. So these are the possible states of the abstract machine, and these are the rules we have for going from one thing to another. Right? So we have 3 rules. Number 1, if true, then T2 else T3 evaluates to T2. If false, then T2 else T3 evaluates to T3. These rules shall be referred to as E if true and E if false. E stands for evaluation. Our third rule is a little bit interesting. If we take as a premise that T1 evaluates to T1 prime, we may conclude that if T1 then T2 else T3 evaluates to if T prime then T2 else T3. So, if we have it already established that T1 evaluates to T1 prime, we can perform a substitution from T1 to T1 prime. There you go. It would be cool if I used reveal.js. No. His stupid flippy animations give me a headache. No, I'm sorry, but you'll have to pry Beamer from my cold, dead hands. You know, I color code my slides based on what courses I do. It's just for me, the color coding. Anyway, so let's break this down. In the left-hand column, we see 2 syntactic specifications. The first is restating the terms we are interested in, particularly those related to Booleans and Boolean operations. The second defines a subset of terms called values, which are the possible final results of evaluation. What is or is not a value and how you get there is going to become increasingly important once we begin to reason about the correctness and the soundness of our evaluation rules. The right-hand column defines an evaluation relation on terms. Written T implies T prime, or that shouldn't be implies. Oh my god. Shoot. Alright. T evaluates to T prime in one step. This relation is defined by the following 3 rules of inference. That's the wrong arrow. I can't believe I got the wrong arrow. Christ almighty. That's better. So, important distinction. Like, in this course, you can, like, double arrow is implication, Single arrow is evaluation. Yes, I know you can disable the slide animation. I like Beamer. I'm going to use Beamer. I'm going to continue to use Beamer until I die. I've decided that this is my comfortable level of a technology. So yeah. So our evaluation relation is single arrow. This arrow. I'm going to pronounce it as evaluates to. Pretty much everything remaining until we hit arithmetic is involved in one way or another in proving various properties of this evaluation relation. So it is a relation in the proper sense of the term, right? It is a pair, it is a pair of terms, right? That's the way that a relation is defined. So, inference rules. Let's examine our rules of inference in detail, starting with if true, then T2, else T3 evaluates to T2. If our conditional expression is a literal truth value, we can simplify the expression to whatever term is represented by T2. Oh, and one more thing about all of these people who do their slides in Reveal.js. They all use minted for their code, like for putting code in the middle of the slides. They use minted, and minted is inferior to listing. Minted is inferior to listing. Fight me. Nothing minted does, like there's nothing minted can do that listing doesn't do better. It's just not as new, so people think it's not as good, but it is. So, if our conditional expression is a literal truth value, we can simplify the expression to whatever the term is whatever T2 is. So, you know, this works the same way as you might expect an if statement to work. If this is true, then you take this one. Otherwise, you take that one. Similarly for the second rule. A literal false value can simply simplify the if statement to just the else branch term. This, you know, this is your intuition about how the semantics of an if statement works, which, you know, shouldn't be new to anybody. Good. If org mode does listing, then you should do that because minted is trash. So, the third evaluation rule, if, is somewhat less straightforward. So, we have, once again, T1 evaluates to T1 prime. That gives us if T1 evaluates to if T1 prime. This is a substitution. We can evaluate T1 to T1. If we can evaluate T1 to T1 prime, we can substitute the guard term of an if expression to T prime, assuming it was T1 originally. In fact, we can use a different abstract machine to, I guess I did like a bad find and replace or something. Sorry about this, folks. I'll update the slides after lecture. Right. Arrow. Compile. There we go. Wonderful. There we go. We can use a different abstract machine to establish T1 evaluates to T1 prime. In terms of implementation, what this looks like in terms of implementation, what this essentially means is that when your execution hits an if statement with a term that has not been fully evaluated, you're allowed to spawn a new instance of that evaluation function in order to evaluate the guard expression, right? And then that will tell you, like, that's how you get from T1 to T1 prime, right? Is you need to create a new instance of the evaluation expression that will bring you there. Once you've done that, you can perform your substitution. You can think of this as the abstract machine spawning an instance of itself in order to evaluate the guard expression. Yes. Note the absence of similar rules for the true and false branches of the if expression. So this is an intentional design decision. You may be saying, well, I'm looking at the semantic, and I notice that you have a substitution rule for the guard expression. Where's my substitution rule for T2 and T3? Why isn't that there? It seems conspicuous by its absence. And there's a reason for that. So what we're in effect doing is we're setting up a deductive system, right? With its own axioms and rules and things. Its own axioms and rules of inference. But we're not being, our design effort is not going into elaborating all possible transformations that we could think of, right? As we're going to see, what we actually want to shoot for is the minimal set of rules and terms that we need, because that vastly simplifies the proofs. And it means that certain properties hold when otherwise they wouldn't hold. So, oh, that's a good question, but I'll answer it once I'm done this rant. So, with respect to... So the reason we do this is because then our semantics have a built-in order of evaluation, right? So if you have multiple rules, like if you have, let's say you had a situation where you had if-then-else, T1, T2, and T3 all could be evaluated. Which rule do you pick, right? If you have rules for substituting all three of those, which do you pick, right? It's ambiguous, and the one thing that you don't want in a language definition is ambiguity. Otherwise, you might as well be doing something in natural language, like God. So, here's a question. Is T1 prime a literal Boolean or just a simpler expression? It's just a simpler expression. If T1 was if T1 was a term that evaluated to a literal truth value, then, that would be, you would substitute the literal truth value, but you shouldn't think about it that way. Remember, we're dealing with small step semantics, right? So, under small step semantics, this arrow always means one step towards the value, or one step of evaluation. For Booleans, what it actually means is it means one application of one of these three rules, and nothing else. That's a very good question. Very good to establish that. It's the bool result after a conditional expression. Yeah. So there you go. So this, T1 prime does not necessarily mean final result. We haven't quite established a notion of finality yet. Right now, we're just talking about, we're talking about single step, right? So it could be another if X, then Y, else Z. Yes. Yeah, exactly. Yeah, thank you, Joe. That was actually a very, very important point, and I'm sure a lot of people will appreciate you asking that question. Because that's actually one of the very important conceptual points to get about one-step evaluation. As we're going to see, once we get into talking about whether this evaluation will terminate, we'll need to introduce the concept of a multi-step evaluation, which is, multiple single-step evaluations chained together. But for now, we're talking about one, right? So, the one-step evaluation relation. Our evaluation relation, arrow, is defined as the smallest binary relation on terms, satisfying the three rules given above. When a pair, T, T prime, is in our is in our evaluation relation, we say that the evaluation statement t evaluates to t prime is derivable. So we're going to be talking in terms of derivation. By smallest, you guys probably know what smallest means now, more rigorously. By smallest, we mean that the relation contains no pairs other than those derived from instances of our inference rules. Since there is an infinite number of terms, there is also an infinite number of instances of the inference rules, and an infinite number of pairs in our evaluation relation. You should not let that scare you, though. And just because a set is infinite doesn't mean that we can't compare the size of it to the size of another set, by the way. Although a language with more terms is equally infinite, it has a much greater degree of expressivity. It has a much larger number of possible languages or possible programs, even if both have, it is definitely a larger infinity. Which is, strange to say, but, you have to kind of let go of this elementary school understanding of infinity that it just swallows up everything and can't be compared. So, we can demonstrate the derivability of a given pair using formal derivation. So, this is formal in the Dr. Farmer sense. There's some interesting stuff in the chat. Sorry for slowing you down, but why wasn't the same type of rule defined for... Yes. Yeah, okay, we're going to get to that when we talk about ambiguity. But, so, the reason that we don't have similar rules similar to this one for T2 and T3 is because if we had them, we wouldn't be able to unambiguously determine what the next evaluation rule should be. We would have more rules, it would give us too many options. What a very, very important property that we want to maintain for all of our languages is called determinacy. We have a whole section on it, establishing determinacy. But essentially, if you had the ability to substitute T1, T2, or T3, if all of them were substitutable, which one do you pick, right? It makes it ambiguous, and we want to avoid ambiguity at all costs because it costs us quite a lot, mathematically speaking. A lot of things can no longer be said to be true if we can't establish that the language is deterministic. And fortunately, this is why I said we want to go for the minimum viable set of rules that establish the language's semantics. You don't want to just be throwing rules in there willy-nilly, because you might break something. Yes. So, is it because they don't get simplified until they are semantically needed? Yeah, it's kind of similar to laziness in Haskell. We don't need to have... So it turns out we don't need to have simplification rules for T2 and T3 because they will be simplified once the if expression is dealt with, right? So there's no need to do them in advance. And even if you do them in advance, you don't know which branch it's going to be until you evaluate the if expression, so it's not as efficient anyway. As you work inwards, the T... Yeah. Couldn't we order the rules for T2 and T3 like PEDMES? Well, once you start in you're adding a layer of complexity there that's unnecessary. So basically the question is, could we establish the ability to perform substitutions on the else branch, for example, but just imply an ordering between our different evaluation rules? So in Project 1, when you're going to be implementing all of this in Haskell, it's going to be necessary for you to create an ordering between the different evaluation rules, just because that's the way that Haskell works. However, from the logic's standpoint, you're introducing something that's not necessary and might be destructive to some of our properties. So what you would be doing, I think, essentially, is encapsulating all of our other rules in a meta rule, which would say, if this one is applicable, do this one. If not, do that one. If that one is applicable, do it. Otherwise, do the next one. And then you'd have, like, X number of rules filtered through this highly complex expression. We don't need to. There's nothing to be gained by it at this level. You get, like, if you keep the number of rules minimized, then it makes it much easier to reason about the system, which as we're going to see. So anyway, we can demonstrate the derivability of a given pair using formal derivation. The textbook uses inference tree style proofs, which I think if you remember what they look like, they look like an inference rule with like several levels. But I'll show you a picture of one quickly from the textbook if I can find one quickly. Yeah. So that right there. There we go. See, it's not important that you should be able to read that, but you see how it's like, multiple inference rules stacked on top of each other? That's the style that they use. Yeah. Yes, as Henry says, Occam's razor. Occam's razor states that the simpler solution is generally preferable. So, in our case, we're going to be using deductive style proofs because they fit better on the slide. But, you guys were hassling me on giving you guys traditional proofs where you were expecting formal proofs. So here are some actual formal proofs in the Dr. Farmer sense. So now that we have a set of terms defined and a set of rules defined, that functions as a deductive system, right? So to show that one term may be derived from another, that can be proven now using deductive logic. You can prove it now with, something approximating a natural deduction style proof, which is what I'm doing here. So, consider the following UAE expression. If true, then if false, else true. Let's set t to the inner if expression so the derivation fits on the page. So I'm performing a slight substitution so that this actually fits. So t is if false, then false, else false. We prove the results of the evaluation as follows. If we start, if true, then t, else true. And we have that's our premise. We have t is if false, then false, else false. So we can apply. We must have we must have t because we can apply e if true on 1, right? 1 is our premise. We apply the rule e if true. We get t as the result. From t, if false, then false, else false. I suppose I could have just put that there, but oh well. If false on 2 yields false. Therefore, we can say that if true, else, then t, else true, evaluates to false. There you go. A very simple example evaluation. Obviously, the computer, when you build a machine to do this, it's going to look a little bit differently than a natural deduction proof, but at various points it may be useful to be able to prove that one thing evaluates to another, and this is a good mechanism for doing it. So there you go. We do have some formal proofs in this class. both formal and rigorous. Example 2. If true, then false, else true, then true, else false. We'll take this middle bit again and assign it to t. So, this is to demonstrate how the substitution works, right? So we start with if t, then true, else false, right? We assume t. We create t as a hypothesis. From that, we can derive false because e if true on 2, right? If true applies to t again because, the guard expression is true. So we can then derive false. So from the fact that we assumed t and we got false, we can say t evaluates to false. We can then use if on premises 1 and 4 to derive if false, then true, else false. And of course, that will evaluate to false. I think I skipped a step there. Yeah, I skipped a step there. I'll fix that in the slides. Let me just write that down. Skipped step, page 16, looked like fool on stream. Good. So, hopefully that makes sense to y'all. Are there any questions about why that should be, any questions about that? Give me a thumbs up if there are no questions. What is the assumption? Okay. How did I go from 4 to 5? Okay, so 2 questions, individual. I will address them individually. So remember from natural deduction, right? If you're trying to establish A implies B, you take A as a hypothesis, you work the natural deduction through, and try to get B as a result. If you can get B as a result, then you can use if introduction, or you can use implication introduction to say A implies B. This is the same thing that's going on here. So we assume T to be the case. We use rules on it to derive false. We can then conclude that T evaluates to false. It's like a sub machine. It's like you have a sub deduction going on inside of it. The point that I'm trying to make here is that this is kind of this is like a side note to the to this larger proof, right? That's why I'm using the flag style, right? Yeah, I'm missing E false. Yeah, thank you, Pacific Cod. So the way that you go from 4 to 5 is using E if on 1 and 4. So if you recall our E if rule, this guy, if we have T1 evaluating to T1 prime, then we can perform a substitution if T1, then if T1 prime. Here, we have established that T evaluates to false. So we can replace the T here with the false, because we have a rule that allows us to do that. You can't do anything if you don't have a rule that allows you to do it. So here's a question from Stephen. If we were to write this in a computer program, would it stop once fully evaluated, false in this case, or would it need to return the whole e-intro statement? No, it would stop at false. For sure. The purpose of this is to show you that we can perform reasoning using this system of deduction outside of a computer context. This is so far, like, only marginally related to, you know, how you would implement this. But, yeah. Yeah, like in an actual computer system, what this would look like is you would have this statement, right? It would detect that this term was not fully evaluated. It would run a subroutine to evaluate that expression, substitute it into this guy, then evaluate that guy to false, and then that would be used by whatever it was that was, you know, using it, right? Like evaluation expression in a proper programming language is always at the behest of something, right? It's always something that needs that expression evaluated. It's not nothing occurs in a vacuum, right? So it's 21, so I don't have time for my last 2 slides of this section. But yeah, anyway, if you have any more questions, please put them in the chat right now. And otherwise, I'll see you guys on Friday. And if you decide to swing by office hours, I'll be having office hours tomorrow. So there you go. It's off the screen. Nuts. I think people are confused about the meaning of assume and in assume induction hypothesis. Okay, I could talk about that for a moment. There we go. So what is it that what do you do when you make an assumption? Okay. So to make an assumption, when you make an assumption when you're trying to prove something, it's for the purposes of establishing a fact and establishing the consequences of the fact so that you can, like, normally there will be some use to showing A implies B, right? I'm going to come back to A implies B because this is the most simple, that's the most simple version of this, right? So assume. So, okay. assume what about t? I see. Okay, Pacific Cod is saying, like, so assume t is true, assume t evaluates to true, assume t is valid in the system, assume t is valid in this system is closest to it. So it's most like saying this t exists, let's reason about it. Let's assume this t exists, let's reason about it. Oh, look, this t just happens to be exactly the same t that allows us to perform this substitution. Isn't that convenient? Now I get to use my rule. Now I get to finish my proof. Yeah, so, like, assume derivable? No, it's like hypothesis. T is a hypothesis. So let me see if I can explain this in terms of natural deduction. So proof of transitivity. So the transitive property is A implies B and B implies C implies A implies C, right? This is the transitive property. But have you ever wondered, like, why? Right? So, if we do a deductive proof of this, one, yeah, it's so we have to take this as a hypothesis. So we have to say we are taking it for the moment true that A implies B and B implies C. From that, we can determine, 1, that A implies B, and 2, we can determine that B implies C. These are both facts that we have, right? So, let me think. It's been a while since I've done this. Yeah! Okay, so our goal is to show that A implies C, right? So we introduce a hypothesis A, right? We introduce A as a hypothesis. I was trying to emphasize it with those dashes, but that's just stupid. Normally you'd tab it out, so let's tab it out. There we go. So this is like 4.1 in this proof. So we introduce A as a hypothesis. 4.2, since we have A and we have A implies B, we can therefore conclude B, right? Since we have B and we have B implies C up here, we can say C. Now, this is a subproof, right? This is all self-contained. Once we're finished this, none of these statements still hold, right? This is like a sub-process, a sub-program, right? So, from the fact that we hypothesized A and we derived C, we can therefore conclude, 4, that A implies C, and then QED. So that's the proof of the transitive property as applied to implication. This is normally called premise. No, premise is something different. This is a premise, right? So, okay. So properly, like if you wanted to use proper logical form, you'd have the turnstile character here, right? So what I'm doing is I'm saying, you know, what am I doing here? I'm saying when you have like a top level implication, that's the same as doing a turnstile here. So A implies B and B implies C. From that we can prove A implies C. Another way of writing this would be A implies B, comma, B implies C. That proves A implies C. So the point is that in order to prove this implication here, I have to introduce A as a hypothesis and then try to conclude C. That's not a premise. This is a premise, right? This is a hypothesis. We sometimes say assume, but it's a hypothesis. It's not a premise. Those are different things. At least according to the logic that I am used to. It's entirely probable that different people have different ways of referring to these artifacts, but hopefully that explicates what the heck it is I'm talking about. Is that a... I see I don't have very many viewers left. Alright. So that's what I'm talking about, yeah? Okay. Well, I think that's everything for today, so if you guys are all logicked out for today, I think I'm going to log off here. Thank you very much for your time and attention, and we'll see you again. We'll see you guys again on Friday. Bye-bye.